Good day, viewers. Welcome back to our YouTube channel, Smart Edu TV. If you are new to this channel, click on the subscription button and turn on the notification bell so that you can be informed whenever a new video is released. For our old subscribers, thank you for staying tuned. Today, we are going to be looking at thermodynamics. In our previous classes, we've seen what we mean by the scales of temperature, how to convert from one scale to another, and how to solve problems that's related to scales of temperature. Today, we are going to be moving to the thermodynamics proper. What do we mean by thermodynamics? What do we mean by thermodynamics? As we all know, thermodynamics is simply the study of the relationship that exists between it and other forms of energy. The study of the relationship that exists between it and other forms of energy. That is what thermodynamics is all about. The study of that relationship that exists between it and other forms of energy. We can't talk about thermodynamics without talking about universe. What do we mean by universe? This universe we are talking about, it consists of two parts. It consists of two parts. And those two parts are the systems and surroundings. These are what makes up the universe. In thermodynamics, the universe is made up of two parts, and those parts are systems and surroundings. What do we mean by systems in thermodynamics? A system is a region with a given boundary under thermodynamic investigation. A system is a region with a given boundary that is under thermodynamic investigation. In thermodynamics, that thing we are studying is what is called systems. What we are studying in thermodynamics is called systems. For the surroundings, that other part that we are left out, that we don't study, is called what? Surroundings. So in thermodynamics, what we study is the systems, and that in which we do not study is the surrounding. Don't forget, a system is simply a region with a given boundary that is under thermodynamic investigation. That is what we mean by systems. These systems we are talking about can be what? Further classified into three. We can classify systems into what? Three. The first one is what? The open system. The open what? System. We also have what? The closed system. And we have what? Isolated system. So these are the three classes of what? Systems under thermodynamics. So I'm going to be giving you in form of what? In form of a table. These are the systems. Let's see what happens to the what? To the energy, or we call it heat. And also, we want to see what happens to the what? To the matter or mass. Let's see what happens to what? To mass or matter. Okay, we said that what? Under thermodynamics, systems is further classified into three. We have the open system, the closed system, and the isolated system. What do we mean by open system? When is a system said to be opened? What do we mean by what? Open system. An open system in thermodynamics is a system that allows the exchange of heat or energy and matter between itself and the surroundings. It allows the exchange of what? Energy and matter between itself and the surrounding. That is what we mean by open system. It allows the exchange of energy and matter between itself and surrounding. For a closed system is a system that allows the exchange of heat but not matter. It allows the exchange of heat but not matter between itself and the surrounding. A closed system is a system that allows the exchange of heat but not matter between itself and what? Surroundings. And the third one here, we call it what? The isolated system. What do we mean by isolated system? When is a system said to be isolated? An isolated system is a system that do not allow both the exchange of energy and matter between itself and surrounding. It do not allow both energy and matter, the exchange of energy and matter between itself and surrounding. That is what we mean by isolated systems. So these are the classification of systems under our thermodynamics. Don't forget, in open system, it is a system that allows the exchange of energy and matter between itself and the surroundings. And a good example of these, of open system, is when we have an open pot of soup. An open pot of soup. What happens in an open pot of soup? An open pot of soup, it means that something can be added inside that pot. And also, the vapors of the soup can also escape to the surroundings. That is what we mean by an open system. In that open pot of soup, water can be added, salt can be added, flavors can be added to that pot of soup. And also, when it boils, the vapors of that soup can actually escape to the surroundings. That is a good example of an open system. For a closed system, we can also use a good example of a closed pot of soup. What happens in a closed pot of soup? In a closed pot of soup, once it's closed, nothing can come from the surrounding inside that pot, because it's already closed. It's sealed. Nothing can come from the surrounding inside that pot without being opened. But what happens when it boils? When that soup boils inside that pot, inside that closed pot? When the soup boils, the vapors of that soup can escape into the surroundings, even without somebody opening the pot. The vapors will find its way to escape into the surroundings. That is a good example of a closed system. For an isolated system, we can consider the case of a thermoflask. We can consider the case of the thermoflask. We all know flask. The flask, we use flask to preserve water, temperature of water, to a particular period of time that we want to use that water. So the essence of that flask is that once the hot water is being poured inside that flask, the flask will be closed. And once the flask is closed, the heat that is inside that flask will not be able to escape to the surrounding. And also, that of the surrounding will not be able to come inside that flask, simply because it is closed. So because of that, we can use that as a good example of an isolated system. This is is possible because that flask we are talking about is large. So the essence of larging a flask is to preserve the heat, to preserve the temperature of that water or of something that we are putting inside that flask. That is the essence of the larging. It doesn't allow the heat to quickly escape to the surrounding, and also it doesn't allow the surrounding temperature to come inside that flask. So that's a good example of an isolated system is the thermoflask. So this is what we mean by systems in thermodynamics. Don't forget, we classify systems into three. The first one is the open system that allows the exchange of heat and matter. The second type is the closed system that allows the exchange of energy but not matter. And the last type is the isolated system that do not allow both the exchange of heat and matter between itself and the surroundings. Okay, so the next we are going to be looking at is thermodynamic properties. Thermodynamic properties. What do we mean by thermodynamic properties? What do we mean by thermodynamic properties? Thermodynamic properties are those physical properties that can be used to describe a thermodynamic system. Thermodynamic properties are those physical properties that can be used to describe a thermodynamic system. These thermodynamic properties we are talking about are classified into two. The first of them is called we have the intensive property and also the extensive property. Number one, intensive property. What are intensive properties? What are intensive properties? Intensive properties are those properties whose value do not depend on the size of the system. Intensive properties are those physical properties whose value do not depend on the size of the system. The value of that property do not depend on the size of the system. And a good example of intensive property is, let's say what, the color of a cloth. Or let's say what, look at this paper, everybody. This is a white paper. This is what, a white paper. If I cut small portion of this paper, what do we notice? We notice that what, they still maintain the same color. They still maintain what, the same color. This is a good example of intensive property. The value do not depend on the size of the system. You can see. So a good example is what? Color of the what? Of a white paper. Color of the what? White paper. Another good example of that is temperature. Temperature. Another good example is density. So all these are called an intensive properties because their value do not depend on the size of the what? System. Their value do not depend on the size of the system. Number two, we have the extensive property. What do we mean by extensive properties? What are extensive properties? Extensive properties are those physical properties whose value depend on the size of the system. They are those physical properties whose value depend on the size of the what? System. Example of extensive properties include mass, volume. You can see all these, their value depends on the size of that system. So this is what we mean by what? Extensive properties. Their value depends on the size of the system. But for the intensive property, their value do not depend on the size of the what? System. Their value do not depend on the size of the what? System. So these are the what? Thermodynamic properties under thermodynamics. They are just two, the intensive property and also the extensive property. So the next we are going to be looking at is thermodynamic functions. Thermodynamic functions. What are thermodynamic functions? Thermodynamic functions are also those functions that can also be used to describe a thermodynamic system. Thermodynamic functions are those functions that can also be used to describe a thermodynamic what? Systems. They are those functions that we can use to describe a thermodynamic what? System. Example of this function include pressure, volume, temperature, work done, internal energy, quantity of heat. All these, entropy, all these gives you energy. All these are what? Thermodynamic what? Functions. They are those functions that can be used to describe a thermodynamic system. This thermodynamic function we are talking about is also classified into two. It is also classified into what? Two. The first one is called the state function. The state what? Function. For the state function, their function whose value depends on the initial and final state of a system. Their value depends on the initial and final state of the what? Of a system. Example, pressure, volume and what? Temperature. They are what? Their state function because their value depends on the initial and final state of the system. We call them state function. The second class we have what? We have the what? Part function. What are what? Part function under thermodynamics. Part functions are those functions whose value depend on the path taken by a system. Their value depends on the path taken by a thermodynamic system to have arrived at their final state. To have arrived at their what? At their final state. Here we are interested in the path taken by a thermodynamic system to have arrived at their final state. This is what we mean by path function. This is what we mean by path function. An example of what? Of a path function is, for instance, movement from Nigeria to India. Movement from what? From Nigeria to what? India. Don't forget, we see that what? Their value depends on the what? On the path taken by that system. That system wants to move from where to where? From Nigeria to what? New Delhi in India. How can we move? We have got different options that we can explore to move from where to where? From Nigeria to India. Number one, we can either what? Explore what? Transportation by air. We can what? Travel by what? By air. Number two, we can also what? Travel by what? By sea. We can also travel by what? By sea. And also the third option, you can also what? Travel by what? By land. So any of these options can what? Can lead us from Nigeria to what? India. But the best for us is what? To move what? By air. Irrespective of what? Of the path that we take. We are interested in what? In that path that is being taken from the initial state to what? To the final path. The path it has taken, that was from what? From where it is starting from to where it is what? Stopping at. So these are what we mean by what? Path function. Their value depends on the path taken by a thermodynamic system. Their value depends on the path taken by a thermodynamic what? System. Under the path function, we have to what? Know how to what? Make some little what? Calculations that involves work done. This is very important. This is what? Very important. We have to know how to what? Calculate what? The path taken by a thermodynamic system in calculating what? The work done by that system. For example, we can have, let's take this example. So let me write it on the board. In this question, what's calculate the work done? We are still trying to explain what the path function, the path that is taken by a thermodynamic system to arrive at its final destination. Example, calculate the work done. Calculate the work done by an ideal gas. By an ideal gas while going from state A to state C. In each of the following processes. In each of the following processes. Number one, A, D, C. Number two, A, B, C. And number three, A, C. According to what? To this diagram. So the diagram is drawn for us. The diagram is already drawn for us. B, C, A, D. Don't forget, these are pressure and these are what? Volume. So we call this PV diagram. So here corresponds to a given what? Volume. So let's call the volume here as what? Volume A, and what? Here, volume C or volume D. And the pressure here, let's call it what? Pressure C, which is also the same as what? Pressure what? B. And pressure here, let's call it pressure A, or we call it what? Pressure D. They mean the same thing. You can see they are on the same line. Okay? So in this question, we want to what? Calculate work done. We want to what? Calculate work done by this system. They have already what? Shown the path that is being taken by that system. All these arrows shows what? The corresponding path that the system is what is undergoing as it moves from one state to another. So here we want to calculate what? Work done. We know that generally our work done is let's say what? Pressure times change in volume. In thermodynamics, generally the formula for work done is pressure times change in volume. Pressure times what? Change in what? Volume. That is the higher volume minus what? Lower volume. That is what we mean by change in volume. So now I want to apply this formula in solving these different what? Processes. The first one is the process from where to where? From A to what? ADC. Number one, I want to calculate work done from where to where? ADC. Work done along what? A, D, and C. For me to what? To move towards ADC, it is that what? I'll first move from where to where? From A to D, then also from where to where? From D to what? C. You can see the arrow has shown it clearly. I can't just move from what? From A to C. No, I'll first move from where to where? From A to D, then from D to what? To C. So this gives us what? ADC. Moving from A to D, and the final movement from what? From D to what? C. Which implies that what? Our work done from where to where? From A to D, plus the work done from where to where? From D to C. So this gives us what? Work done along what? ADC. Our work done from what? A to D is giving us, our work done from A to D is giving us, don't forget, our work done is what? Pressure times what? Changing volume. Let's look at what? A to D. The pressure here, I can call it what? Pressure A or pressure D. It's still the same thing. Either I call it pressure A or I call it what? Pressure what? D. Since they are what? Along the same line, there is a constant pressure. Times our change in volume. Our change in volume here is what? The higher volume minus lower volume, that is VC minus what? VA. VC minus what? Minus VA. Plus, what happens to the work done along here? Along DC. Work done along what? DC. Look at it. Work done along what? DC. Its own pressure. I can call it what? Pressure A or pressure D. They still mean the same thing. I can call it what? Pressure A into its own volume along where? Along D to what? To C. The volume what? Remain constant. Can see. It's still what? VC. That means I will say that what? VC minus another what? VC. Because there is no change in volume. That is why anytime you are calculating work done and there is what? There is a constant volume. That work done along that part is what? 0. Because the what? Change in volume here from D to C can only be what? VC. Along the path D to what? C. I'm interested what in this part D to what? C. So the work done is what? VC. So VC minus VC will give me what? 0. The 0 times PA will also give me what? 0. So at the end of the day, my work done along ADC will now be what? PA into VC minus what? VA. The whole of this becomes what? 0. Is that right? The whole of this becomes what? 0. So it implies that at the end of the day, so all these guys becomes what? 0. So my what? My work done along what? AD is now what? PA into what? VC, volume along C, minus volume along A. That is the work done along what? ADC. You can see the way what we analyze that system. Going to what? To the second question. I want to calculate the work done along which part? Along ABC. How do we calculate work done along what? ABC. Let's go back to what? To our diagram. A, B, and C. It means for me to what? Calculate work done along A, B, C. It simply means that I must calculate the work done along where to where? Along A to B plus the work done along B to what? C. The work done along what? A to B plus the work done along B to what? C. So let's do the same thing here. I want to calculate work done along A to what? B. Let's calculate work done. Don't forget, our work done is still what? P times what? Change the what? B. I want to calculate work done along A, B, C. Along A, B, C. This is going to give me, don't forget, work done along here, A to B, along A, B, plus the work done along B, C. Plus the work done along what? B, C. So, in calculating that, my work done, this implies, let's look at work done along what? A to B. The pressure along A to B, I can call it what? PA. The pressure, I can call it what? PA. Don't forget PA or PD. You can see they are still on the same line. So either I call it PA or I call it what? PD. Why? Pressure at A is the same pressure as D times our change in volume. Our change in volume along what? AB. You can see, let's look at this again. A to B is A to B occurs at where? At constant volume VA. There is no change in volume along what? A to what? B. You can see it's just a single line and the volume is what? VA. That means V higher will be what? VA minus another what? VA. Why? There is no change in what? Volume. At constant pressure, there is no change in what? Volume. Is that correct? What I see here is that what? At this pressure, I didn't see what? Any change in volume. So that means what? Here, my work done is what? PA is what? VA minus what? Another what? VA. This is giving what? 0 plus work done along BC, along BC. Work done along what? BC. Is on pressure. Let me call it what? Pressure along C. Multiplied by the change in volume. Along what? B to what? C. Our change in volume, we trace it to what? To the volume. It should now be what? VC minus VA. VC minus what? VA. You can see our change in volume is now what? VC, V higher minus what? V lower, VA. At the end of the day, the whole of this is also what? Gone. Why? At constant volume, there is no change in what? The work done is what? 0. At constant volume, under thermodynamics, our work done is 0. That is why our work done along ABC is now given as what? PC into VC minus VA. Looking at the last one. The last one here, I also calculate the work done along what? Part AC. Along part what? AC. Let's look at this very well. Along part A to what? C. How do we calculate work done along what? Part A to what? To C. How can we get to what? A to C? I have different options. So what? To move from what? From point A to point C. The first option is that what? I should move from what? A, B, C, or the second option, I should move from here A, D, C. So these are the two options I have to what? To explore in order to move from what? From point A to point C. So in that case, I'm going to be looking at what? At the two options. I'm going to be looking at the two what? Options. Moving from what? From here to here, from A to what? Work done along what? AC. Will now be what? Work done along what? AB plus work done along what? BC. That's what? Option 1. Or the second option. Work done along what? AD plus work done along what? DC. So these are what the two options that I can use to move from point A to what? To point C. And also in thermodynamics, anytime we are solving what? Systems, or means positive, it means what? Plus, addition. Just like what? In the case of probability. So also, when solving what? Thermodynamic system, or means what? Addition. It means you are going to what? Add this result to what? To this result. But looking at this very well, This is what? This is our general formula. Now, let's look at that formula very well. From A, B, C. If you look at it, A, B, C, considering what? AC as the destination, it gives a particular shape. A, B, C, considering what? A to C as the final destination, it gives what? A particular what? Shape, which is the shape of the what? Triangle. Similarly, ADC, considering the fact that what? That point AC is also what? A final destination. This also gives another what? Triangle. That means in solving this, I'm going to use the what? The formula for calculating the area of triangle. I'm going to use the formula for calculating the area of what? Triangle. Don't forget, area of triangle is what? Half, then now calculate for the what? For the work done. Half the work done here plus half the work done in the second phase. So in doing that, our work done along AC will now be equal to, so let's start, half into what? Now let's look at it. Work done along what? A what? AB. P dB. Change in volume is what? Is 0 along AB. That is what? 0. Plus work done along BC. Along B to what? To C. Work done along what? B to what? To C. Is what? P times change in what? Volume. Our pressure along B to C. Let's call it what? PC. Times change in what? Volume. Its own change in volume with what? BC minus what? VA. That's what the first phase. That's what the first phase. Plus the work done in the what? In the second phase. Don't forget half into. Now let's look at what work done along what? Along AD. Along A to what? To D. Our PdB. Our pressure here is what? PA. Pressure along A times its own change in volume. BC minus what? VA. Can you see that? Plus the second one, which is work done along what? DC. Work done along DC at constant volume is also what? 0. The work done along DC is also what? 0. Why? At constant volume, there is no work done. So our PdB there is what? 0. So at the end of the day, I'm going to have, I can what? Write them as something like this. So at the end of the day, I am going to have half is common to what? To both of them. Half is common to both of them into, I have what? PC plus what? PA. Then for the volume. For the volume, I have what? VC minus what? VA is what? Is also what? Common. VC minus what? VA. So this is what? The formula for calculating the work done along point A to what? C. Work done along point what? A to what? C. So for what? For a real problem, all this pressure will be, the value will be given to you, and also this volume, its value will be also what? Be given to you. So let's look at one or two examples on how we can what? Use this to solve problems. How can we use this to solve what? Problems. So I'm going to what? Draw a particular triangle for you. That is what? Let's say it's similar to this. So let's draw a particular triangle. So looking at this what? This system, I will label it. Can use another format to label it, so that's not a problem. Let's say don't forget this is what? Volume, and here is what? Pressure. This is a PV diagram. So don't forget this is A, let's say A, B, C, D, or let's say B, C, so that we follow the same format. B, C, A, and D. So let's follow the same format. I'll change the volume here. Let's call this what? 5 meter cube. Let's call this what? 2 meter cube. Our pressure here Let's call this what? Let's say 10 Pascal, and the pressure here. Let's call this. Let's call this 15 Pascal. 15 what? Pascal. Okay. So looking at this what PV diagram, calculate the work done in the following process. Number one, work done along AD. Number two, work done along what? Let's say ABC. Work done along what? ABC. Okay. Work done along what? ABC. Okay, solution. So let's start with the first one. Our work done along AD is going to be equal to, don't forget our formula for work done. Our work done is what? P times what? Change in V. Don't forget P times what? Times what? Change in what? Volume. Our pressure times change in what? Volume. So that our work done along A to D will be, what is the pressure along A to D? Our pressure is what? 10 Pascal. 10 times the change in volume along A to D. Our change in volume is what? 5 meter cube minus 2 meter cube. So at the end of the day, this will give us what? 30. 5 minus 6 is 3 times 10. That's what? 30 what? Joules. 30 what? Joules. 30 what? Joules. Work done is measured in what? Joules. So we have what? 30 what? Joules. Along the path A to what? To D. For the second one, let's look at the work done along ABC. Work done along path ABC. Work done along path ABC is simply what? The work done along path A to B plus the work done along path what? B to C. Work done along path A to B plus the work done along path what? B to what? C. You can see work done along what? A, B, C. In this case, don't forget our what? A to C is not the what? The final destination. Our A to C is not what? The final destination. That is why we cannot call this the what? A triangle. Simply because our point A to C is not the final destination. Rather, we just want to calculate the work done in moving from where? From path what? Along path what? A, B, and C. Which can be what? Gotten by moving from where to where? From A to B plus movements from where to where? From B to what? C. Our movements from A to B. From A to B, don't forget PdV. This should give us what? Pressure times change in volume at constant volume. Our work done is what? 0. Our work done is what? 0 at constant volume. Plus movements from what? From B to what? To C. Movements from B to C. Our work done here is going to be what? Work done along what? B to what? C. The pressure along B to C, which is what? 15. Pressure times change in volume along here to be along B to what? C. Change is what? The line B to C to the what? To the volume part. This is what? Corresponds to 5 meter cube. Why this B corresponds to what? To 2 meter cube. So I'm adding 5 minus 2. So this will give me what? 5 minus 2 is what? 3. 15 times 3 will give us what? 45. 45 joules. That is the work done along path A to what? B. This is how we solve a path functions related questions that involve us to calculate work done. Path function related question that involves us to calculate work done.